random variable, and then we build partial sums. So each time we go through this loop, we add the next probability. And the value, the interval, we stop when this number nu is between the current partial sum and the next partial sum, if it falls within that interval. This is called inversion by sequential search. So you add up until your partial sum exceeds your random number. And then that index, the left and the, if you compare left and the right interval endpoint, that index then is the index that is being sampled. So you can see that non-uniform sampling takes some work. Of course, in MATLAB, you have commands for that. In R, you have commands for that. But at least once I knew this, I thought, okay, fine. Now I know how it's done computationally. So there are different ways of sampling. So we want a sampling matrix. It's usually the sampling matrix has few rows because we really want only the few rows to make the computation much cheaper. So we can do uniform sampling with replacement. This means you pick an integer, put the corresponding row with that index in the sampling matrix, so it can extract that row, throw this back into the bucket, and then do it again. So that means you could sample the same index twice or thrice. So that means that this sampling matrix would have the same row. It would extract the same row from the matrix twice or thrice. And then of course, because you're only extracting, say, C rows, you have to make up for it with a fudge factor, which is the total number of rows over the number of rows you extracted. And that's what gives us our estimator. So the Gram product of the sampling matrix gives us the identity. Well, now you could think, well, if I can sample the same row twice or thrice, that's not really good if I want to get columns that are linearly independent. So it would seem at first that sampling without replacement is a lot better. So there, what you do is you take your indices from 1 to m, you perform a random permutation of these indices, so you get k1 through km, and then you just pick the first C of these indices and put them as in the sampling matrix. So the corresponding columns of the identity, so it can extract the corresponding columns of the matrix A. Third method is Bernoulli sampling. So there you get a square matrix. So for each diagonal element with probability C over M, you either pick the corresponding row of the identity matrix, and with probability 1 minus C over M, you just put a 0 row there. So this is going to be an m by n matrix. And we don't know in advance how many non-zero rows this matrix has, how many non-zero diagonal elements. However, in expectation, on average, this thing has C non-zero diagonal elements. However, this can be a big square matrix. So alternatively, you can simulate Bernoulli sampling. If you sample C tilde, the number of rows from 1 through m, with a binomial probability, and then you do sampling without replacement. So from a computational point of view, that gives the same. Okay, so here are 3 sampling methods. So I'm going to do a comparison of the 3 methods, and the matrix I'm going to look at is a matrix with 10,000 rows and 5 columns. And now you're going to say, oh, why does she pick such a weird matrix? They don't occur in practice. So many rows and so few columns. Well, yes, they do. And if you have a matrix that's almost square, with basically as many columns as you have rows, and you want to sample and get linearly independent columns, you basically have to sample the whole matrix. So these randomized algorithms are not good for matrices that are almost square. You need a lot of redundancy. So many rows are a lot of redundancy, and that's why sampling succeeds, because of the many rows, you have redundancy, and it sort of doesn't matter what you pick. I think that's the intuition behind it. So we have matrices with with orthonormal columns, and so I'm going to show a plot where we sample anywhere between 5 and 10,000 rows. We need at least 5 rows because we have 5 columns, otherwise we don't have a chance at getting linearly independent columns. And 10,000, well, that's the number of rows. And we are going to plot 2 things. The percentage of matrices that are rank deficient, because they're going to be useless, because they're going to result in solutions that are not that are biased estimator. And rank deficient in floating point arithmetic means that the condition number is greater or equal to 10 to the 16. So that's rank deficiency in IEEE double precision. If we manage to get a full rank matrix, then for that matrix, we plot its condition number. So this is for the sampled matrix. If that is full rank, we can plot the condition number. Okay, so here you see 3 rows of panels. This is for sampling with replacement, without and Bernoulli. It doesn't matter really what is shown. The 3 panels, the 3 rows look sort of the same. And that's the message that I want to get across. So if you want to look closely, what do we have here? On the horizontal axis, we have the number of samples. So here we sampled 2,000 rows, 4,000, 6,000, 8,000. So you see that for sampling with replacement, as soon as we sampled 2,000 rows, about 20% of the rows, the probability that we get a rank deficient matrix is 0. It stays 0. The same for the other 2 sampling methods. Here we plot the condition numbers of the matrices where we succeeded. Those are matrices that have full column rank. And here the units are 10 to the 0, which is 1, and 10 to the 1, which is 10. A condition number is never below 1. A condition number never makes things better. Life is not fair. Condition number only amplifies. It doesn't diminish. So condition number below 10 is paradise. So if you manage to get a sampled matrix that has linearly independent columns, the condition number is just wonderful. It's below 10. And that is the same for all 3 sampling methods. So because all 3 sampling methods, so this is anecdotal evidence, we did extensive experiments in the paper, but this is just to illustrate that they don't really differ. There's little difference for small amounts of sampling. Therefore, we may as well do sampling with replacement because it's the easiest method to implement. You can do it in parallel and all that. It doesn't hurt us if we sample a row twice or thrice. That's what that says. Okay, so let's look at the randomized least squares regression. So here's our least squares problem. We have a tall and skinny matrix with linearly independent columns. A direct method on a dense matrix would require n square operation. So linear in the large dimension, quadratic in the small dimension. So some people have done a classification of randomized algorithms, and it's very simple. They are randomized algorithms that do row-wise sampling or compression. That means you pick a few rows, what we just did before. That way you decrease the large dimension from M to C. So after compression, if we don't count how much it costs to sample, then the problem now has only C rows down from M rows. You can also do column-wise compression. You come then from the right-hand side. So you work on the small dimension, which doesn't look very promising, especially if the small dimension is real small. So you reduce from n squared to c squared, but you still have the large dimension. However, in the special case where you're not doing compression, you just have a non-singular matrix here. That can be used as a preconditioner to accelerate iterative methods, and that's what we will look at. So there's a lot of existing work on randomized algorithms, row-wise, column-wise compression, preconditioning, statistical properties. So a lot of work. So let's look at row-wise compression. So here's one of the early works. Oh no, it got stuck. Okay, fine. So this is a paper by Drineas, Kanan, and Mahoney. So we have our sampling matrix. So out of M rows, this is the identity matrix. It has N, M, canonical vectors. And we want to pick C of those for our sampling matrix. So our sampling matrix consists of C rows of this identity matrix. And how to determine which rows? We look at the indices which go from 1 to M, and we sample the indices uniformly with probability 1 over M, independently, that's important, and with replacement. So that means some of these indices here in the sampling matrix can be the same. And because we don't have the full matrix, we have our fudge factor to make sure that the gram product is in expectation the identity. Okay, so this is the algorithm. So let's just look at.
There is a question from Simeon. He asked, can you do both row-wise and column-wise on the same matrix?
Yes, you could do that, but I wouldn't want to do the analysis. Well, okay, so people do that actually. They do, especially for other types of decomposition, CUR decomposition, they come from the right and they come from the left. Yes, you can do that. So for least squares problems, yes, there is a, Michael Mahoney and Michael Saunders have a software package, LSRN. And I think they can do both sampling methods, I mean, row-wise and column-wise compression. However, analyzing that becomes a lot harder. And we will work on the right-hand side, not by compressing, but by having a non-singular preconditioner, because that is a safe way. But the short answer to your question, Simeon, is yes, you can do that. However, finding out under what circumstances that is beneficial, that analysis is not going to be as trivial.
Thank you.
Mm-hmm. So here's another baby example again. So here's the matrix again. Clearly, it has non-linearly independent columns. I want to sample 2 rows of this matrix independently and with replacement. So M over C here is 4 over C, which is square root of 2. And I can choose any row of the 4x4 identity matrix here, any row of the 4x4 identity matrix here. It is real easy to sample matrices that are rank deficient and not so good. So for example, it could be that the sampling matrix has the first row of the identity and the first row of the identity again, because we do sampling with replacement. So it picks out this thing twice, and this is clearly a rank deficient matrix. Or else the sampling matrix could decide to pick the 4th row and the 2nd row. So the 4th row is all zeros and the 2nd row is this. Well, again, we have a rank deficient matrix. So it's with some, that shows you it's really easy to sample rank deficient matrices. However, if you take the unbiased estimator of the Gram product, it ends up being the 4x4 identity matrix. So in expectation, but expectations are often too hopeful. And that's why we have tail bounds for the probabilities. So here is then the row sampling algorithm. You input the matrix, the right-hand side, and the sampling amount. And then you construct your sample. So this is a conceptual algorithm. I mean, you wouldn't really construct the sampling matrix because this is just a pointer, right? But just to make it, to illustrate the ideas, let's suppose we construct the sampling matrix explicitly. So each row of the sampling matrix is sampled uniformly, independently, and with replacement. And then we put the corresponding row of the identity there, so it can extract the corresponding matrix of the row A. So here we have a much smaller problem now with C rows instead of M. And now we just do the usual QR decomposition, whatever, to solve that smaller problem. Okay, so how do you attack the error due to randomization? How do you do that? So usually what people have been doing is a derivation in 2 steps. In the first step, you derive a structural bound. You treat the sampling matrix as a fixed deterministic perturbation and do a deterministic analysis like what we do in 723, and carry that as far as possible. And then once you can't go any further, then you use a probabilistic bound where you treat this matrix as a random matrix and then take recourse to matrix concentration inequalities. So here's a structural bound for the absolute error. This is our exact solution. And the randomized solution, well, it's the sampled matrix and the sampled right-hand side. Now, just for this talk, let's assume we are in the good case where the sampled matrix has the same full rank as the original matrix, just to make things easy. So with the QR decomposition, so all we want to do is now derive an error bound, right? So on paper, we can do anything. So we could assume we have a QR decomposition of A and put this in there. And then our error, our absolute error, the solution of the randomized problem minus the exact solution can be written this way. It may look a little involved, but this is the least squares residual. So the right-hand side cannot get closer to the left-hand side than this. This is an oblique projector onto the column space of A. So, and if the sampled residual is not that far away from the original residual, we can get a bound on the absolute error. So the solution of the randomized problem minus the exact solution in terms of the vicinity of the true residual to the sampled one, in terms of the inverse of A, you have that even for linear systems, that orthogonal, that oblique projector, and the least squares residual. So we think in terms of relative bounds, where we divide the absolute error by the quantity we want, because floating point arithmetic is characterized by relative error. So you compare the error to the size of the quantity you want. And so if we have a relative error on the left, we need relative quantities on the right. So this is a normalized least squares residual, where we normalize the residual by the matrix and by the solution. We get the condition number here, the amount by which a matrix stretches a unit norm vector times the amount by which it shrinks one. That's what we usually have for linear systems, and this oblique projector. So I don't want to get into perturbation theory. However, this relative error bound is better than the typical relative error bound we have from deterministic perturbations, because this is a multiplicative perturbation. And usually what we do in 523 and 723 is we have additive perturbation, and then we get the square of the condition number multiplying the residual. So if your condition number is 10 to the 8, in IEEE arithmetic, it's fine. But then if you have the square of the condition number, that's 10 to the 16, and then the problem is basically a singular problem. So the sensitivity to these multiplicative perturbations is less than the sensitivity to the usual additive perturbations, which is how we characterize round-off error. So that leaves this thing here, this oblique projector. We will get a probabilistic bound for this. And this bound for this has to also take care of this epsilon, because we don't know in advance how far the sampled residual is from the true residual. So, and we also have to take care of the fact that the sampled matrix should have full column rank. So that also, this is all the responsibility of this probabilistic bound. Before we go there, can I talk about, okay. So, okay, let me go there. So for the analysis, what we are going to assume that in the background lurking, we have a QR decomposition. It's not computed, but it's being there in the background lurking. And then the idea is that because A is equal to QR, extracting rows from A is the same as extracting rows from Q, because the S here affects A and the S here affects Q. So whatever rows it extracts from A, the analogous rows are being extracted from Q. So sampling rows from A amounts to sampling rows of Q. And that really simplifies the analysis, because instead of thinking about all kinds of matrices A with linearly independent columns, it suffices to think about matrices Q with orthonormal columns. That makes the problem conceptually a lot simpler. However, before this analysis, can I please look at the randomized solver for sparse matrices, because that thing faces the same problem. So here we have, we want to do now it's a little bit in the spirit of Semyon's question. Here we have our least squares problem. Instead of sampling from the right, from the left, we come from the right. However, we are not doing compression. We are coming with a non-singular matrix. So the small dimension is not compressed. It's a non-singular matrix. And we are hoping that we can find a non-singular matrix so that the condition number of this thing is small, so that LSQR converges fast, and then that we can retrieve our original solution cheaply. That's the requirements we have for the preconditioner. So let's gauge our expectations. What would the ideal preconditioner be? Well, suppose we had a QR factorization, and we would use this R as a preconditioner. So if we multiply by the inverse of R, we get AR inverse, and that leaves Q. Q has orthonormal columns. It has a condition number equal to 1. It's perfect. LSQR converges in one iteration. However, this is exactly what we are trying to avoid in the first place, right? Because a QR decomposition is exceedingly expensive. So that we cannot compute the preconditioner that way. However, it gives us some ideas. So a randomized preconditioner says, well, I'm still going to do a QR decomposition, but not of the whole matrix, only of a few rows of the matrix. So we are constructing something that goes on the right-hand side of the matrix. I shouldn't do this. I shouldn't move back and forth. It goes on the right-hand side of the matrix, but the way we compute it is, I'm sorry, I moved too much. The way we compute it is by sampling rows of A. So we sample a few rows of A, that gives us a short matrix. We do a QR decomposition. So Q sub S, R sub S refer to the QR of the sampled matrix. This thing still has orthonormal columns, and this still is triangular. So let's use this triangular matrix then as a preconditioner. And the operation count now is this matrix has only C columns down from N columns. So then solving the sample problem is a lot cheaper. Okay, here's a little pitiful picture. So this is our original problem, the tall and skinny matrix A. And this is the QR decomposition we would get from it. However, if we just sample the purple rows here, we get a much shorter matrix. And you can see the QR decomposition is cheaper just because the matrices involved have smaller dimension. Okay, so this is what the idea behind blend and pick, an algorithm by Avron, Maimonkov, and Toledo, and it is really fast. It's competitive with the LA-PAC routines. So we input a random matrix with linearly independent columns of sampling amount, and then the algorithm consists of 2 steps. In the first step, we construct our preconditioner, the thing that accelerates the iterative method. So we sampled C rows of A, and then we do the QR decomposition of the smaller matrix. Then we use this triangular matrix here as a preconditioner on the right for our least squares problem. We solve this with our iterative method LSQR. Once we are done, we retrieve our original solution. All the while, we hope and pray that this condition number is really close to 1, so we get fast convergence here. Okay. So how do we get from sampling to condition numbers? And that was really a neat idea that Chaim Avron and Sivan Toledo have. So again, as I mentioned before, we have 2 QR factorizations. We have the one we compute from the sampled matrix, the smaller factorization. However, lurking in the background, not being computed, just being there up there in the sky, we still on paper can write the QR factorization of the full matrix on paper, not computed on paper. Then as we have observed before, sampling rows from A is the same as sampling rows from Q because S attacks A and attacks Q. This matrix R is non-singular. It doesn't disturb the rank. Therefore, the rank of the sampled A matrix is the same as the rank of the sampled Q matrix. And it's not hard to show that the condition number of the preconditioned matrix is the condition number of the sampled matrix with orthonormal columns. So that means if we want to analyze things, it suffices to look at orthonormal matrices and sample rows from them, a conceptually much simpler problem. Okay, so what can you expect? So here again, I have a little toy baby problem. We have a matrix with orthonormal columns. It has 8 rows and 2 columns. And you see it's the first 2 columns of the 8x8 identity matrix. Then here I have another matrix. It has all ones, and in here it has ones in the first half, minus ones in the second half. So these are 2 columns from a Hadamard matrix. And then of course you have to normalize by 1 over square root of 8. So if you had to pick 2 rows from each of these matrices, and your goal was to get a matrix that has rank 2, so a little 2x2 non-singular matrix, which matrix would be easier to sample from, this or this? Think about it. If you can randomly sample 2 rows, well, you might hit this one and this one. You have a real large chance of hitting a 0 row. However, here, if you get 1 row in the first half and 1 row in the second half, you're all set. You have a non-singular matrix. So, and this is how you quantify this. In this case, the row norms squared of this matrix are 1 and 1. And this is as large as they can get because this is an orthonormal matrix. The column norms are 1, hence the row norms cannot be larger. They can be at most 1. All the other rows have norm 0. In this case here, all rows have the same norm because the magnitudes, the absolute values of the matrix elements are the same. And the norms, P norms, don't care about signs, right? So in this case, all rows, in this case, the matrix has all rows with the same norm. And in this case, where the mass of the matrix is concentrated here, 2 rows have large norm and everybody else has 0 norm. So this matrix has a mass that's uniformly distributed. So uniformly distributed, so it sort of doesn't matter what you pick, you get something good. So, and this is, so looking at the largest row norm, which is 1 here and which is 1/4 here, is a way to distinguish which matrices are easy for sampling and which matrices are not. And we cannot just bound the row norms by 1, because that way we cannot, all the orthonormal matrices look the same. We need a way to distinguish them. Our way to distinguish them is to compute the row norms and then pick the largest one and then compare. So the largest row norm distinguishes different matrices, and it is used to quantify the difficulty of sampling. Okay, so here comes a bound for our probabilistic bound. What we are going to do is, this is our sampled matrix. We are going to look at its deviation from orthonormality. And now you're thinking, oh, why does she do this? This has nothing to do with anything. Well, this is the deviation from orthonormality. If SQ were a matrix with orthonormal columns, this thing would be 0. While chances are it isn't. However, this is a bound for a matrix, and perturbation theory tells us if this deviation from orthonormality is bounded by epsilon, then simultaneously all singular values squared are bounded by 1 minus epsilon and 1 plus epsilon above, simultaneously for all singular values. We don't need a union bound. That really saves us. So by trying to bound this deviation from orthonormality, we get bounds on singular values. And now it's like an infomercial where they tell you, oh, and you get this, and you get that, and if you phone in the next 5 minutes, you get that too. Well, what you get is you get a bound on the smallest singular value that bounds it away from 0. That guarantees that the left inverse exists. Here then is a bound on the norm of the left inverse that you get, and here then is a bound on the condition number that you get. So by just bounding the deviation from orthonormality, you get bounds on all the important quantities. Okay, how do you do that? Well, here's a standalone non-commutative matrix Bernstein concentration inequalities that Ben Recht has been doing a lot of work in this area. So this standalone inequality, what does it say? What does it assume? It assumes that you have independent random matrices. These are not matrices whose elements are 0, 1, normal 0, 1. These are not matrices whose elements are uniform 0, 1. These are just matrix valued random variables with expectation 0. You need the matrices to be bounded. And because the expectation is 0, this is the matrix variance, right? It's non-commutative, so this is the square, right, in both directions. Then you find yourself an error tolerance that you can tolerate, and then we can cook up a failure probability. Let's go to that later, so that we can bound the sum of these random matrices by epsilon with this amount of success probability. Because these guys have expected value 0, so does the sum. So this is really the deviation of this sum from the mean. And this holds with probability 1 minus delta. What goes into delta? The matrix dimension. So the smaller the dimension of the matrix, the smaller the failure probability. The bound on the matrices and the bound on the variance. So the smaller these two bounds, the less wiggle room there is, and the smaller the failure probability. And then, of course, the error tolerance. The less demanding you are, the smaller the failure probability. So we apply this bound to get a bound on the condition number for a matrix with orthonormal columns. So I have to watch the time now. I have 5 more minutes and then it's it. So our matrix, we characterize it by the largest row norm squared. We decide how many rows we want to sample. We decide how much error we can tolerate. And then we have our formula for the failure probability. It's in terms of the small dimension of the matrix outside the exponential. Inside the exponential, we have C over M. That is the ratio of rows with the percentage of rows we sample. We have the largest row norm. So this thing is small if the mu is small, and then of course the error. So with this failure probability, 1 minus delta is a success probability, we get our bound on the condition number. So we can look at the tightness of this condition number bound, and it's a pretty good bound. So for example, if we sample 10%, at most 10% of the rows. So our matrix has 10,000 rows, we sample at most 1,000. I plotted here the condition numbers and here the bound. This is 10, this is 1. Our bound holds starting about 93. So you can see, considering this is 10, then this here is 5. So our bound captures the true condition numbers within it with the same magnitude. And that's all you want from a condition number. You don't want it to 16 digits. You just want to know the condition number to an order of magnitude. And if we sample more, then you may think, oh, this picture looks worse, but no. This is 1.4. Condition numbers of 1.4 are unheard of. So our bound gives 1.4. The exact condition numbers are 1.2. So this is an extremely good bound. So to summarize, for our condition number bound, it gives us the correct magnitude. It's informative even for very small matrix dimensions. So it doesn't need an asymptotic regime. It's already informative for small matrix dimensions and stringent success probabilities. We used a success probability of 0.99 here, and that was conservative. Now we are using a success probability of 1 minus 10 to the minus 16. It implies a lower bound on the number of sampled rows, and that's just a sanity check that gives us the connection to the coupon collectors problem. And the bound depends on the what is called coherence, the largest row norm of Q. And that reveals the distribution of mass in the matrix. So coherence is a concept. So it's the largest row norm of a matrix with orthonormal columns. Its lower bound is the aspect ratio of the dimensions. Its upper bound is 1. Maximal coherence is a matrix that has at least one row of the identity. The mass is concentrated in a single element. Minimal coherence comes, say, from the columns of a Hadamard matrix, where the mass is totally uniformly distributed. Coherence measures the correlation with a standard canonical basis, and it reflects the difficulties of sampling. And you can extend the definition of coherence to general matrices and subspaces. And this concept actually originated in compressed sensing in a paper by Donahoe and Ho, where they look at the coherence of the standard basis with other bases. And then other people have taken it up for matrix completion, estimation of coherence. Avon, Maimunkov, and Toledo were the first to use it for least squares, and fast approximation of coherence isn't really fast. And if we look at the oh yeah, I need one more minute, then I'm done. If we look at the effect of coherence on sampling, we look at two matrices. One that is 1.5 of optimal coherence, and one where the coherence is 100 times larger. And we plot the usual thing. So here's the matrix with good coherence. This is the failure, meaning we get a rank deficient matrix. The only time we have a failure is when we sample exactly 5 rows. We have 5 columns. Other than that, we always get full rank matrices, and the condition numbers are lower than 4. That's great. So the full rank matrices are perfectly conditioned. However, if we increase the coherence by a factor of 100, meaning the mass is more concentrated or not so distributed anymore, then most of the time we don't get a full rank matrix. Most of the time we fail. In the few instances where we get a full rank matrix, yeah, the condition number is great, it's below 10. But most of the matrices are rank deficient and not really useful for least square solver. So the conclusion is that if we have a matrix with low coherence, then sampling is easy. The mass of the matrix is uniformly distributed. It doesn't really matter what you pick. If we have a matrix with high coherence, the mass is concentrated. Sampling is really hard because you have to be really, really lucky to get anything good. So here are now my summary. So a few takeaways here. So when we have this least squares problem and we want to solve this, then sampling is effective if A has good coherence. The mass of its orthonormal basis is uniformly distributed. Matrix concentration inequalities are an important ingredient to get good bounds. We've looked at a safe randomized solver where the randomization was confined to a preconditioner. We solved the original problem. We didn't discard any rows. We just accelerated the original problem. So that is a safe way of using randomization in the preconditioner. We did not discuss improving the coherence of A with fast matrix multiplication by random FFTs, Hadamard matrices, or cosine transforms. And there are a number of research questions. The numerical behavior of randomized algorithms and floating point arithmetic is difficult because things are not reproducible. There's the effect of sampling on the statistical model uncertainty. We want flexible preconditioners that adapt to the problem and say change in every iteration when you have a least squares problem in the inner loop of an optimization problem. And then we also have to think about regularization for ill-posed problems. So if you're interested in this, there are a number of surveys and books. There's the book by Luc Devroy. A good undergraduate textbook for randomized algorithms is, for undergraduate computer science book is the one by Mitzenmacher and Upfall, where Shinin has a pretty recent book on high-dimensional probability, and Joel Trop is always good at explaining things. In terms of matrix concentration inequality, randomized algorithms, and Michael Mahoney has a monograph on randomized algorithms that's much more practical. So this is a more theoretical one, and this is the practical complement. And these are some of the papers that I referenced. Thank you very much for your attention.
Thank you very much. Are there any questions? While people thinking could ask a question, I would like to ask you, you mentioned that the thin and tall matrices appear in applications. Could you give some examples where they would appear?
So for example, in statistics, where the columns represent variables and the rows represent observations. So, variables could be height, like hair color. So you have your few variables, and then you want to sample the population. So each row corresponds to a person, and you record the variable values for each person. So often that way, when you have many observations and a few variables, that's when you end up with these tall matrices.
Yeah, thank you. More questions, please.
It's okay, it's Friday afternoon.
This has been the talk that I understood the most out of all the talks I've heard this whole semester. That's good. This isn't even my area. So that's
Appreciate
good.
That. Thank you.
Yeah, comments are also welcome, not only questions.
Well, thank you very much for coming on a Friday afternoon. Appreciate it.
Thank you very much for giving very good talk. Thank you.
Bye.
Bye.